So there are two ways to report the precision. One is absolute deviation, is the difference between experiment and the true value. There's an example here. If we make a measurement on a resistor, that's we know the resistance is 6.83 ohms. We measured that resistor at 6.83 ohms, and the resistor was certified to provide 6.80 ohms. Then the absolute deviation will be the difference between these two, the measurement and the certified result, which should be the true value. So that gives us the 0.03 ohms. So that has a unit, and that's absolute difference between these two. If we want to look at the relative deviation, that's the percentage difference. So basically, we use the absolute deviation. So that's 0.03 ohms divided by the certified true value. So that will give us a 0.44% difference. So usually in most of the scientific measurement, the percentage deviation is more important because, for example, I'll show you a measurement here. Look at this value. Can you guess what that is? It's a really large value, and it's a speed. So it's roughly 300,000 kilometers per second. That's a very large speed. Can you guess what that is? That's speed of light. So it's really fast, 300,000 kilometers per second. The NIST reported the measurement of 299,781 plus minus 10 kilometers per second in 1906. So in 1920, the American scientist Albert Michelson corrected that measurement. So his measurement is 299,796 plus minus 4 kilometers per second. Reduce the deviation, enhance the precision for the light of speed. And that results get Albert Michelson the Nobel Prize. So we'll review some of the significant figures calculation we'll use throughout this semester. Remember, I gave you that URL link in the other PowerPoint that you can use that one to look at some of the rules of significant figures. I'll post those two URL links on Canvas as well. We can review the significant figure rules here. The first one is all non-zero numbers are significant. So that's pretty straightforward rule. So 613 has 3, and the 1, 2, 3, 4, 5, 6. This number has 6 sigfigs. Zeros located between non-zero digits are significant. So any zeros between non-zero numbers are significant. So for this one has 4, this one has 3, and no matter how many zeros in between, as long as there are numbers in front and numbers in the end, then all the zero count. So this one has 16 sigfigs. Okay, rule number 3, the trailing zeros. So when the zeros at the end are significant only if the number contains a decimal point. Otherwise, they are insignificant. Let's look at some example here. This one, 5.640. So it has 1, 2, 3, 4, right? Because it has a decimal point. So we'll count the last zero as well. And for this number, if I put this decimal point after all the zeros, then we need to count all of these 4 zeros. And so this one has 6 sigfigs. And for this one, it doesn't have a decimal point. And we'll say this one has only 2 sigfigs. Rule number 4, zeros to the left of the first non-zero digit, they are insignificant. Okay, so they are only placeholders. So for this one, all zeros here, they have no significance. Their role is only to occupy those places. So they don't count as significant figures. So for this one, we only have 3. And for this one, we have 2. And no matter how many zeros in front, we only have 2 for this one. Let's work on a couple examples. So remember the scientific expression, how to express the number. This is 120,000 if only need 2 sig figs. We can write this as 1.2 times 10 to the 5th, right? So here in this expression, we only count the digit in here as the significant figures. We don't count anything in this number here, the power here. We have 1 and 2, so that's only 2 sig figs. And that express the number of 120,000, right? So this one is a little tricky. How many sig figs if I say I have a pH measurement of 9.00? It's not 3. Why it's not 3? I mean, if you look at the rule from 1 to 5, it's what tells me that should be 3, right? That has something to do with the log. That's important. So what's pH? If you remember, pH is minus log concentration of H, right? So that's P, that's H. And so if it's a log, then what's a 9 here? What's the 9? And of course it has a minus sign, so it's a minus 9. What's the minus 9 here? The 9 only representing the power part. So it has nothing to do with the sig fig. So the hydrogen concentration in this case should be 1.0 times 10 to the power of minus 9 molar. The 9 doesn't count into the significant figures. When I say the pH value is 9.00, significant figures for that measurement is only 2. So let's try this example. We've seen that quite a bit from newspapers. We'll see, okay, we have a COVID vaccine and the vaccine efficacy was 91.6%. Then based on that result, can we guess how many people were probably infected during the trial? Well, let me ask you this. Do you know how to get this efficacy data? What's the definition of this efficacy? In the third phase trial, people are separated into 2 groups. One is control group, one is treated group. So in the end, after a certain period of time, there may be a fewer number of people get contracted with the COVID in the treated group, and maybe more people get infected in the control group. So let's say 1 people in the treated group got COVID, and 100 people in the control group got COVID. Then we take the ratio of these 2. That's 1%, right? 1 over 100, that's 1%. Use 100% minus that 1%. That'll give the efficacy. So in this case, when you read on the newspaper broadcast, it says the vaccine efficacy was 91.6. It had the 3 sig figs. If you know the process, then that means at least we have 100 people that's infected in the treated group. So we can generate a number with 3 sig figs. If your rating or vaccine efficacy was 91%, then that's 2 sig figs. That meaning their patient pool is very limited. So they probably only get 10, 20 people infected. When the patient pool is very limited, probably telling you that the result is not as robust as a result with more sig figs.